Okay, here's lesson 24, quadratic formula and discriminant. The quadratic formula is another way to solve for x-intercepts. This is the fourth method of the four that we are reviewing in this class. The other ones that we have already covered are solving by factoring, solving by the square root method, and solving by completing the square. Today is the final way of understanding how we can find x-intercepts. The discriminant is a way to tell the nature of the roots. The discriminant is part of the quadratic formula. As you see in green and in purple, the quadratic formula is everything in that statement. X equals negative b plus or minus square root b squared minus 4ac all over 2a. But the discriminant, which is where I can determine if I have two real rational roots, two irrational real roots, one rational root, which is also a double root, or zero real roots, meaning I have two imaginary roots. This is an important aspect of the quadratic formula because it can actually help us out understanding what our graph would look like. On the next slide, we have the discriminant and the cases. The discriminant is known as d equals b squared minus 4ac. In the first case, which is the first row, if the discriminant is greater than 0, any number above 0, then there's two cases that could occur. If the discriminant is a positive perfect squared number, then I'm going to have two real rational roots. If the discriminant is a non-perfect squared number, then I'm going to have two real irrational roots. Now that's because a perfect square, right, if it's under the square root, and say I have the number of 49, right, if I were to take the square root of 49, which is a perfect squared number, then I'd have the number of 7. I'm going to go back a slide. So if I put the number of 49 in that b squared minus 4ac, do you agree that I would have negative b plus or minus 7 divided by 2a? Well, that's going to give me two real rational roots, meaning I can graph them on the x-axis. No estimation is possible. Whereas if I get the discriminant being a non-perfect squared number, something like the number of 21, well, then I'm going to have two real irrational roots because, going back to the last slide, if the discriminant was b squared minus 4ac and I got 21, can you take the square root of 21? The calculator can, but we can't. Therefore, I would have to graph that as the square root of 21 plus or minus, so I'd have one on each side, but that's not a real rational number. I would have to guesstimate that x-intercept. Okay, the next case. Say the discriminant is actually the number of 0. That tells me the nature of the roots indicates that I have one real rational root where that root is actually a double root. Remember, a double root is something that bounces off that x-axis one time, which is where that root is hitting. Lastly, if the discriminant is less than 0, then I will have two complex roots, also known as the imaginary roots. You could call them non-real roots, complex roots, imaginary roots. They're all going to be the same. Okay, so let's get into some examples where we can understand this a little clearer. Example 1, I have x minus 1 quantity times x plus 6, the quantity of, is equal to 1. In order to do this series of questions, standard form, discriminant, nature of roots, number of intercepts, solutions, and sketching, I need to put this in standard form. So I'm going to need to double distribute the parentheses with one another, minus the 1, and set it equal to 0. So as we do that, we get x squared plus 5x minus 6 equals 1. From there, to equal to 0, I would get x squared plus 5x minus 7 equals 0. And this is my standard form. So I'm going to write that in my standard form. X squared plus 5x minus 7 equals 0. The next task I'm tasked with is finding the discriminant. So again, the discriminant is d equals b squared minus 4ac. So I'm going to plug in my numbers. But before I do, maybe I should identify what is a, b, and c, because I'm kind of, it's Thanksgiving break. I forgot a little stuff. So a, remember, is always in front of x squared. So in this case, it's 1. B is always in front of the x, and that number is 5 in this case. And c, the constant by itself in this case, is negative 7. From here, I'm going to plug it into my formula, and I have the parentheses of 5 squared minus 4 times 1 times negative 7, and that's going to give me 25 plus 28, which is a total of 53. My discriminant, d, equals 53. Now, what does that tell me of my nature of the roots? Well, let me go back a slide. 53. It is greater than 0, so I'm in this case for this problem, example 1, right? And this, I then look over and say, is it a perfect square or is it a non-perfect square? 53. 53 is a non-perfect square. So we're in case B. 2 real irrational roots. So I'm going to write that. 2 real irrational roots. Done. The next task is to find the number of intercepts. This one typically tricks students because when we think of intercepts, we typically just go x-intercept. But notice it doesn't clarify. It just says intercepts plural. That means we have y-intercepts and x-intercepts to think about. So in order to do this part of the problem, I'm actually going to throw a sketch of the graph for what I can see. In order to sketch the graph, I need to find the solutions. So I'm going to actually skip the number of intercepts, move to solutions real quick, and let's find those. So for solutions, that means I do x equals my quadratic formula, negative b plus or minus the square root of my discriminant, so 53, all divided by 2 times 1, which is 2. Wait, so that's my solution. Oh, yep, that's true. That is my solution. So I could claim that my solution, set notation, is negative 5 plus or minus the square root of 53, all divided by 2. Set notation, we're done. Now with that means I have 2 solutions, 2 intercepts that are crossing the x-axis because of that plus or minus, right? That plus or minus is really giving me key that there are 2 values there that will be different. So now on to the number of intercepts. Well, I'm going to throw a quick sketch up. Let's see what we got. Now the square root of 53 is somewhere between 6 and 7. No, 7 and 8. Just kidding. 7 and 8 because the square root of 49 is 7. Square root of 64 is 8. So we're somewhere between 7 and 8. And we're going to take 5 and either add 7 or 8 to it or take 5 and subtract 7 to 8 to that. So we're somewhere, positive side, negative side, fantastic, something like that, some x-intercepts. We have negative 5 minus root 53, all divided by 2, and on this one, put x equals, and on this one we got x equals negative 5 plus root 53, good, Weissmuller, divided by 2. Okay, now the a in this case was positive 1, so hopefully you agree with me that the sketch is going to be going up like that. And then I notice, there's an intercept down here, and that would be at negative 7. Remember, as we learned in lesson 25, if we have a c value, this actually indicates a y-intercept, right? Indicates that y-intercept at 0, negative 7. So when it asks me the number of intercepts for this problem, looking at my picture, do you agree that that answer is 3? I have 2 x-intercepts, 1 y-intercept, and we have answered all the questions. Moving on to example 2. Example 2, we have 4x squared equals 3x plus 7. Now typically when we think of standard form, we think of keep the a value as positive. I'm going to do that. So we have 4x squared minus 3x minus 7 equals 0, and that is my standard form equation. From here, I'm going to identify my A's, B's, and C's just so I have that list ready to go when I need them for my quadratic formula. So I would say A is equal to 4, B is equal to -3, and C is equal to -7. As for the discriminant, so that's going to be where we solve that D is equal to B squared minus 4AC. Now let's plug in our A's, B's, and C's, and let's find out what our discriminant's equal to. -3 squared minus 4 times -7. Well, negative squared anything is a positive, so I know that this is 9. -4 times 4 is 16. 16 times -7 may be negative... question mark. We got it. Use your brain. Use your brain. Do you agree it's 112 and it'd be a positive because two negatives make a positive, and we're sitting there with 112. From there, add 112 and 9, we're at 121, and my discriminant is 121. Now thinking back or reviewing real quickly, 121 is a positive number. So we're dealing with, on this one, positive, well, that's going to be case 1 as well. So this is going to be example 2. Example 2 is greater than 0, so that's good. Now, are we case A or case B? Is it a perfect squared number, or is it a non-perfect square? 121, well, that's 11 squared, so we're dealing with case A in this example. Case A for example 2. We have a perfect square. So what do we have? 2 real rational roots. What does that really mean, though, right? 2 real rational roots. Now, once we graph and do that sketch, we'll be able to understand what those really mean. So give us a minute. Let's solve the quadratic. Let's actually find our solutions first. So when we solve for the solutions, let's look at that. That's going to be x equals -b plus or minus the square root of 121, all divided by 2 times 4. When I simplify that, I should get something like 3 plus or minus 11, all divided by 8. Now, this plus or minus in that numerator really means that I could write this as 3 plus 11 divided by 8, and 3 minus 11 divided by 8. So simplify each fraction appropriately. Well, 3 plus 11 is 14 divided by 8. Well, they're both even numbers, so I would say that's 7/4. And 3 minus 11, well, that's -8 divided by 8, produces -1. The number of intercepts we have, we're not there. Solutions, though, we have 2. We could claim that it's set notation, -1, 7/4. Or we could claim, let's write them as intercepts, -1, 0, and 7/4, 0. Now, as for my sketch, so here goes my sketch, right? We have 1, 2 axes, beautiful. Now let's label the x's. We're sitting one at -1, okay, so x equals -1, or 7/4. Now 7/4, 8/4 is 2, so we're a little less than 2, or you could just claim 7/4 works too. Lastly, A is +4, so we know that we're concave up. And last but not least, do you agree that because we have a standard form thing, this is really helpful? This again tells us the y-intercept is -7. So down here, -7. How many total intercepts are there? 3. 2 x-intercepts, 1 y-intercept. And we're moving on to the next example. Example 3. For this example, again, the question is get it in standard form first. So let's distribute, right? We got 8x times 5, or 40x. We have 8x times -x, which is -8x squared, and that equals 50. from here, to put it in standard form, my goal is to always make a positive. That's a personal preference of mine. So 0 equals 8x squared minus 40x plus 50. Now from here, that's our standard form. So I'm going to write that over in standard form. 0 equals 8x squared minus 40x plus 50. The discriminant. Well, how do we find the discriminant again? Discriminant equals b squared minus 4ac. What do I need to identify before I can plug into those things? A, B, and C. So here we go. A, x squared, so that's 8. Bx, so that's negative 40. And C, well, that's 50. So now plug it into your discriminant. You're dealing with negative 40 squared minus 4 times 8 times 50, which equals, well, 40 squared, well, it's 4 times 4 times 100, so that's 1600. And then minus, well, 4 times 8 is 32. 32 50s make 1600. But if you can't think of it like that, which normally I don't either, I think of it like this. 4 can break into 2 times 2. So I would like to take 2 times 8 and then 50 times 2 and do that product, which is where I get 1600 for the second part. Okay, now that's just side math. Going back to the problem. Once I have the discriminant, which, right, 1600 minus 1600 is 0. So I have the discriminant equals 0. So when I then think of the nature of the roots, let me go back to my table. The discriminant equals 0, well, then I'm sitting here. This is example 3. I have the discriminant equals 0, then I only have one real rational root, and I know that it's a double root. So I'm going to go write that. I have one real rational root. And I'm going to write under solutions that it's a double root so that I don't miss that. I'm going to just write it there so I have that there. So then let's find our actual solutions. X equals negative 40 plus or minus the square root of 0, all divided by 2 times 8. Well, that's going to be 40 divided by 16, which, can I simplify that? Yes. I could take 8 out of both of them, and I'm left with 5/2. So my solution to this problem is one x value, which is my goal, nature of the roots, one real rational root, where my solution is 5/2, and I know that it's a double root, so I'm going to scoot that over. Okay. Now, what does this look like, right? What does this actually look like? Let's sketch it out and let's see. If I'm looking at my standard form, I hope you see that we're sitting at a positive 50 as our y-intercept, right? We know that this is our y-intercept at positive 50. Okay, so we have 50, solid. We also know that we have solution happening at 5/2. There's 5/2. So what does our graph look like? Well, it's going to go through the solution of 50, there the intercept, and it's going to bounce at that one rational root because it's only going to hit that x-axis one time. That's what one rational root means. So when I analyze the number of intercepts that this total graph has, I hope you agree it's 2. One y-intercept, one x-intercept, even though it's a double root. It's one intercept. And there's the sketch. Okay, last example of today. Example 4. So we have x squared minus 5, x squared divided by 5, minus x divided by 2, plus 1 equals 0. Now, I'm going to convert this because I don't want to handle fractions when I deal with my discriminant or my solutions, because I'm already dealing with fractions. So I don't want to deal with double fractions on top of each other. So I'm going to get a common denominator, and I'm going to multiply this entire equation by that common denominator so that my a, b, and c are now whole numbers. I hope you agree I would multiply everything by 10. So it's going to be 10 times what I have and then 10 times the other side as well. So 10 times what I have, which equals 0 times 10. Okay, when I multiply this all by 10, I should get something like 2x squared minus 5x plus 10 equals 0. From here, I'm going to find my discriminant. My discriminant's going to be found by d equals b squared minus 4ac. Again, before I find my discriminant, I'm going to identify what is a is 2. What is b? B is negative 5. And what is c? Positive 10. So again, that tells me I'm dealing with the y-intercept at positive 10, right? Key things to remember. Now my discriminant, I'm going to plug it in. I got negative 5 squared minus 4 times 2 times 10. Well, that's going to be 25 minus 4 times 2 is 8. 8 times 10 is 80. Now when I take 25 and minus 80, I think I'm left with negative 55. So now, I got some stuff to fill in. Discriminant, negative 55. Standard form, sure. 2x squared minus 5x plus 10 equals 0. Now, nature of roots is the next question, but I got to go back to my table. So discriminant equals negative 55. So negative 55 means we're less than 0. So this is going to be example 4 down at the bottom. So we're dealing with two complex roots. So let's write that. We're dealing with two complex roots. Okay, so then going on further, let's find the solutions that we have, right? Solutions, we have x equals negative b. Let's clear that 5 up a little. Negative b plus or minus the square root of negative 55, all divided by 4. 2 times 2 is 4. Then we're left with 5 plus or minus I root 55. Forget about those i's, they're in play, divided by 4. Now, is that written as a complex number? But the answer is no, it's not. We have to write it as a complex number. So in order to do that, we have to remember that we have to split our fraction up. So we have 5 divided by 4 plus or minus the square root of 55 divided by 4 and an I at the end. Our solution to this is going to be 5/4 plus or minus the square root of 55 divided by 4, and I at the end, close your brackets. Now, how many intercepts does this graph have? Well, if I'm dealing with complex, meaning I'm not crossing the x-axis at all, and I know that one of my intercepts is at c equals 10, or 10 is my y-intercept, so 0, 10, then I should remember that I have one intercept because only one of them will cross the x or y axis. Folks, that's the lesson on 24. Have a wonderful day. Good job.